So glad you're here. Okay. Very good. So the whole idea of polarity is important now because of as these molecules stick together. Okay? And the thing that sticks molecules together are called intermolecular bonds. And we kind of talked about intermolecular bonds before. When something melts, intermolecular bonds are broken. When something freezes, intermolecular bonds are formed. And this is not going on to the next slide. Let's do this. There we go. So intermolecular forces or intermolecular bonds, it's the same thing. So I'll go ahead and put the word bonds under forces because that's kind of how I usually use intermolecular forces, i.e. bonds. Those are the things that break and are formed as something changes its physical phases, solid, liquid, gas. And like I said, the intermolecular bonds have to do a little bit with polarity, or polarity as a player. So this hopefully looks familiar. I'll draw little boxes underneath each one of these. If I were to draw a box containing a solid, box containing a gas, or box containing a liquid, the solid particles are all stuck together. So here's my solid particles, and I'll go ahead and make green the intermolecular bonds. So it has a high degree of intermolecular bonding. And those are the things that are broken as a solid becomes a liquid. Then down here I'll just skip the liquid for now because it has an intermediate degree of intermolecular bonding. And for gases I'll just go ahead and make them way far apart, and they, if they're behaving ideally, they have no intermolecular bonds. We'll go ahead and give them a lot of motion. And my movies work this semester. In Chem 1, my movies were not working. So let's just check her out. Yay. Oh, see? No, it's not. Hang on, hold that thought. I think I need to change this right here. This one's not so cool, but the other ones are, or some of the other ones are. And there. Yay! Okay, so hopefully we can see a lot of intermolecular bonding, solid, intermediate with a liquid, and no intermolecular bonds with a gas. All right. Wonder how I get it to go back.
Now it says essentially no bonding with the gases, but is there still some small amount that occurs?
The cooler the gas is, the more likely you are to have miscellaneous ones form. Yep, exactly. Good catch. Oh, man. There. Maybe. Okay. Oh, we got another movie.
Matter changes.
Give us some sound here.
Heat increases this motion. The amount of motion dictates how well atoms and molecules can hold on to each other. The less motion there is, the better the hold, and the more solid the matter. When liquid water is cold enough, its molecules arrange in a particular structure and turn to ice. When heated, the vigorous motion of liquid water molecules separates them from one another, and they become an invisible gas.
So I almost don't know which comes first. Is there more motion, so then there's less the intermolecular bonds, or less intermolecular bonds, so there's more motion? but they go hand in hand. Cool. Okay, so I don't know if this sounds familiar, but it takes energy to break those bonds. And as I call it from left to right, as we go from a solid to a liquid or liquid to a gas, we're breaking those intermolecular bonds, and it takes energy. But as we go from left to right and right back to left again, or excuse me, as we go from this way, from right back to left, energy bonds are being formed and energy is being released. I'm not sure why my thing isn't. And we talked about, I remember the energy associated with melting, we call that heat of fusion, and energy associated with evaporation, the heat of vaporization. Okay, and then as you're going, okay, so we add heat. Goodness. And we call that latent heat. As we go from a gas to a liquid to a solid, heat released. And it's also latent heat. Are you serious? Okay, so that's very quantifiable. And I don't know if you remember, but these would be positive enthalpy changes, and these will be negative enthalpy changes. Cool, yay. All right. I'm not sure. Try this way. Oh. It is Monday. Poke at it. Close that one out. All right. I think it's gonna whip into shape for me. So I think that this is gonna be fine, it's just my recordings aren't gonna be right. That's okay. All right. So this is an important slide. Sometimes I pass this out, and I still might, maybe Wednesday, bring you a copy of this because it's important. This is important. And we'll be walking through each one of these. So we have different ways of connecting particles, okay? If both particles is an ion, then that intermolecular bond is an ion-ion intermolecular bond. I know it's weird to call it molecular even though it's an ion, but okay. Now, if it's connecting an ion, a charged particle with something that's like a molecule, but that molecule is polar, we call that an ion dipole intermolecular bond. This would come with mixtures. The next one is hydrogen bonding. These are two molecules that have and we'll talk about what's so special about hydrogen bonding coming up. And then we have ordinary dipole-dipole. It just means that you have two polar molecules that are stuck together, and the thing sticking them together is an ordinary dipole-dipole intermolecular bond. And then we have something that is something that's polar and something that's nonpolar, okay? So we have a dipole-induced dipole thing holding those two pieces of matter together.
Why
And
is it called induced dipole?
Because you basically take something that's nonpolar and there are reasons for this, but something that's nonpolar temporarily, it has induced on it a region of negativeness, a region of positiveness.
That's what I thought.
Yep, it's nonpolar, but you kind of make it temporary polar, and it's induced polarity. And then this last one down here is two nonpolar substances. I just love this lecture because the reason molecules that are not polar can stick together is because they kind of have temporarily regions of negativeness and positiveness, and then they have that intermolecular bond that connects between oppositely charged regions. Okay. The thing in asterisk down here says that the ion dipole, you've got to have a mixture, and the dipole-induced dipole must be talking about a polar, non-polar substance. The other ones could be pure substances, or they could be mixtures. Okay. So, oh, by the way, the reason I think this is so important is, notice over there on the left, is we have strongest at the top and weakest at the bottom. So here as we get going, we're going to be talking about what's so important about strong intermolecular bonds. Well, those are going to be hard to melt, hard to boil, okay? If you have a weak intermolecular bond, they're going to be very volatile. It's going to be boil easily. So that's kind of what we have. That's why it's so important. Okay. So if you're talking about a pure substance, then you kind of limit that list of 6 down to, must be ion-ion, hydrogen bonding, which is a special type of dipole-dipole, or ordinary dipole-dipole, induced dipole-induced dipole. Okay, so we'll start with just the phenomenon that happens between molecules that are polar. So we have these dipole-dipole intermolecular bonds, and it can only happen with 2 polar molecules, whether those 2 polar molecules are the same or whether they're different, you know. I just think that is so cool. So let's see if we can do this a little more smoothly. Let's see.
Hydrogen chloride molecules are polar when HCl molecule.
That wasn't very smooth. Yes, I need to. These movies are worth it, so I'll be going back and forth, I think, a little bit. Let's see, this way. Starting with dipole-dipole.
Hydrogen chloride molecules are polar when HCl molecules in the gas phase are cooled. The kinetic energy of the molecules can no longer overcome the dipole-dipole forces between them. The opposite ends of the molecules attract each other and coalesce to form a liquid.
So to me, it was going from a gas to a liquid. So you saw the repeating HCl, no intermolecular bonds. And then, like we said, how do you get a gas to be a liquid? Well, you cool it down. Energy was released. And we can actually quantify that energy in the latent heat of condensation. Okay, so this is actually just a still image of a dipole molecule. Polar molecules. So dipole-dipole intermolecular bonds only happen with polar molecules. So we've been kind of putting the partially negative, partially positive. And you can see how they're kind of alternating. So if I were going to draw in the intermolecular bonds, they would go like this, dot, 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 dot. You can kind of see how they're oriented. Those are intermolecular bonds. Okay, so we had ion-ion is the strongest. And then of the pure substances, after ion-ion, we have this hydrogen bonding, which is a special type of dipole-dipole. So with hydrogen bonding, you need to have two polar molecules. But the deal is, and I kind of think of it as two conditions. You have to have hydrogen for hydrogen bonding, no duh, right? And your hydrogen needs to be bonded directly to either an oxygen or a nitrogen or a fluorine. So if you find oxygen, nitrogen, or fluorine right there, you can kind of see that they are very electronegative and they're relatively small, which makes them great for this. So actually, as I've drawn this water molecule up here, water can hydrogen bond with itself. What hydrogen bonding does is, we've always known that this is what, partially negative, and we've known that this is partially positive. What hydrogen bonding does is to make it just nice and small and tidy, okay? So it's not that big a deal. I'm gonna go ahead and draw a second water molecule so it can hydrogen bond with itself. So here we go. Here's my second water molecule. So this is partially negative, partially positive, partially positive. So as I draw this connection, not a chemical bond, but an intermolecular bond, that is a hydrogen bond. That's it. Totally it. So there's a water molecule, another water molecule, there's your hydrogen bond between those two molecules. So it has to have a hydrogen. I'm repeating to myself so I remember how this goes. The hydrogen bond, you need to have available hydrogen that is chemically bonded to an oxygen, fluorine, or nitrogen. So ammonia, NH3, it meets that criteria. So here is NH3 and it's pure, hydrogen bonding to itself. And I know in biomolecules, like I think like the helical structure of DNA and RNA, this hydrogen bonding is really important between the rungs, I think. I'm thinking of the amino acids. It's kind of cool. Okay, the simple molecule HF, hydrogen is chemically bonded to a fluorine. So when HF has intermolecular bonds with itself, those are hydrogen bonds. So again, remember, those are right under ion-ion. So it's ion-ion, hydrogen bonds, which is a special dipole-dipole, and then you have dipole-dipole. You have dipole-induced dipole. Cool. Back to water. There's water in its solid phase, and here's water in its liquid phase. So the difference in its liquid phase is some of those intermolecular bonds are broken. Water is so awesome because how it fluffs out when it goes from a liquid to a solid.
So it's because the hydrogen bonding that we have where ice expands?
Yeah, it's related to, and it's the geometry of the bent molecule that orients itself to make that. It's excited. Isn't that cool? I know. So then these slides kind of talk about each one. This is just showing the water molecule. It's showing you water molecule in its solid state. It's exactly like what you said. Oxygen atoms are arranged in a bent hexagonal rings that make these kind of layers.
So does other hydrogen bonding molecules, do they behave the same way? Do they expand?
Kind of, because this is crystalline, you know. I'm not sure. That's my second question of today. I kind of kid that my mom writes everything down. Now I'm starting to write things down. That's a good question. I know there are most liquids, when they transition from a liquid to a solid, most of them get smaller and they don't fluff out like that. But like, do other, like, I'll put NH3 expand. So is that your question? Yeah. Good question. And there it is in its liquid state. Cool. Another video. Now the significance of this video is we have H2S, H2SE, H2TE, and actually H2O. So sulfur, selenium, and tellurium, kind of thinking, yeah, you find them on the periodic table. So basically, we're substituting this something else. And the point is gonna be that if you substitute something in for that oxygen, you no longer have hydrogen bonding. Because that's kind of the crux of the video.
A plot of the boiling points of the group 6A hydrogen compounds shows a trend. Based on this trend, we would expect the boiling point of water to be here. In reality, H2O's boiling point is much higher. This is a consequence of water's stronger hydrogen bonds.
You know, and we'll be talking more about this, but, so, let's see, how do we read this? First off, as I go down, so these are boiling points, okay? If I go down in the boiling point temperature, that means it's easier to boil. If it's easier to boil, that means it has, the bonds are less, okay? So, low bond strength. Okay, and so, this guy up here, this is the heaviest. That's like period, what is that? It's period 5, okay? This gets, selenium gets a little bit lighter, and sulfur is the lightest. Okay. So what we're going to see, and we do see this trend, and we'll talk about this trend later, is that with the lighter size of the sulfur versus the tellurium, we do have lower bond strength, totally. But the reason that H2O is not even less than that is with H2O, finally, we have something very special that only happens with oxygen, nitrogen, and fluorine. We have those hydrogen bonds, which just crazy, it makes it so much harder. The bonds are so much stronger. So that's why H2O is up here, because it's your hydrogen bonding. We're getting there. Okay. So let's see if we can make sense of this. Again, it's kind of like what we looked at before, where each color, the black, the green, the blue, and the red, they have what we call analogous compounds. So, for instance, here's the analogous compounds, H2O, H2S, H2SE, H2TE. We're just basically substituting the oxygen as something else. This is exactly that is exactly the video we watched. If we look at HF, we could substitute instead of a fluorine, we could put a chlorine or we could put a bromine, or we could, wait, what am I going to do? So HF, so we put HCl, that's right, HBr, HI. And the things that fluorine, chlorine, bromine, and iodine have in common is, again, they're the same group. But it's only with HF do we get hydrogen bonding. And H3, the same thing. We could pick, instead of nitrogen, we could put phosphorus or, is that arsenic? Or antimony.
Is there a reason why water is still higher than the other ones, the HF and H3?
Yeah, that's a good question. So these guys, water is still higher. I'm thinking it's probably a little confounded. First off, if you compare this to a water molecule just to the HF, notice that you have two options here, and in HF you just have one. And so that's a player for HF to be less. Do you know what I'm saying? For NH3 though, you have 3, but oxygen is heavier than nitrogen, and so it adds a little bit, so it does, yeah, it does get a little bit kind of hairy. But, so why do you think this last one, the red one, why we have CH4, and instead of a carbon, you could substitute silicon, germanium, or tin? Why don't we see it go up?
Because it's not, the hydrogen isn't bonded to a O after and then.
Perfect, yes, because there's no hydrogen bonding going on because the hydrogen's not bonded to, yep, nitrogen, fluorine, or oxygen. Very good. Another video, it's like video day.
Ice is held together as a solid by hydrogen bonds. When ice melts to liquid water, the regular, relatively open structure of ice collapses. Liquid water can be more efficiently packed and denser than ice.
I'll buy that. Okay. So sticking with our pure substances, induced dipole, and I kind of think like if they want you, for whatever reason, for a mother to go into labor, they induce her, you know. So basically it's bringing something kind of artificial, okay? So to induce a dipole on a nonpolar molecule is to basically kind of put a temporary partially positive, partially negative. So these intermolecular bonds are sometimes called London forces or dispersion forces. So there's 3 names for them, unfortunately. Okay. So one of the things, and I can pick on water if we want to, is as special as, is that, I guess, would that work? I don't know. Pick on something else, something that's a little bit bigger. So I'm going to pick on an alcohol. So I'm going to I'll make it a butanol. I'll give it 4 carbons, a bunch of hydrogens. We'll make it a normal butanol. So the hydroxyl group is over here. Okay, so each of these are H's. Now this isn't the final Lewis structure because I don't have, I'm thinking you could do that maybe. But this actually meets the criteria for hydrogen bonding, doesn't it? Okay, so I can go partially negative, partially positive. Okay, now, and we'll talk more about this later, but this right here, this carbon chain stuff, this actually is it's a non-polar part of a polar molecule. Okay, so.
So is it like half and half almost?
It is. It's kind of, and actually detergents that are great at, like dissolves like, polar, nonpolar, detergents actually have a nonpolar end and a polar end. So it's kind of a both minds. So I picked this as an example because even though we have these great hot spots here, what this slide is saying is actually kind of in the nonpolar region, we kind of at times will induce a dipole, and I don't know, we could actually have a temporary partially positive here and a temporary partially negative here. Just pick those 2 carbons, or hydrogen, I'm not sure, maybe that makes more sense. Make this to a hydrogen. Okay, and if we do that, then we have induced that on there. It's basically electrons are kind of a little bit more over here than over here. And then this thing can line up with another butanol molecule, and then we'd have an intermolecular bond that is induced dipole, induced dipole. So what this says is all substances, even cool ones like this that can hydrogen bond, have this induced dipole going on. So, and this is a good example. This idea of getting a kind of inducing, these are my induced, okay? The bigger this is, the more likely you are to kind of have that separation occur. So the larger the molecule, you're going to see more of these dispersion forces, these induced dipole intermolecular bonds happening.
Because it's just more likely to happen because it's larger.
Yep, yep, exactly. Yep. Okay, so there are 7 diatomic elements, Hofbräu-nickel, okay? And so iodine is one of them, it'd be like I2. But what you would tell me is the I2 molecule has equal electronegativities. That darn thing is very nonpolar. So how do you get I2 to connect to itself? And this is what this video talks about, describes.
An iodine molecule has, on average, an electron cloud that is symmetrically spread over each iodine atom. I2 is not polar. The attractions or repulsions between the atoms of I2 molecules can distort their electron clouds. Dipoles can thereby be induced momentarily in neighboring molecules.
So, you know, that partial negative, partial positive, that's the induced charge. It's weird to think how that works.
Yeah. So it just kind of happens when they get closer to each other.
Mm-hmm. The electron cloud is distorted. Here's a still image of kind of a similar thing going on. Just say that green blob is a nonpolar something, okay? And so I think what this is saying, you say, does it just happen? Well, let's just assume somehow that one of its buddies got a place where it was electron rich and electron deficient. Then what it can do is contaminate the first one. So, yeah. It's kind of like a statistics thing, you know, kind of probability thing, you know. Where are the electrons going to be?
Is there certain non-polar molecules that have higher chances of being induced?
Yep, and my organic chemistry is a little rusty, but that's actually a player in chemical reactions, you know. Cool. Well, this purple is I2, and this orange is Br2. So, again, these molecules are, the only way you get a solid is for intermolecular bonds to form. Okay, so, and the only way you get a liquid is for an intermediate amount of intermolecular bonds to at least form. But the fact that they're hazy, can you imagine this is I2 gas and this is Br2 gas? You're right. Okay, so it's kind of a tenuous sort of, Yep, yep. And this actually goes exactly what you said before, polarizability. So how likely is it to go ahead and have that induced dipole occur? How likely are you to be able to make that happen? So to understand the degree to which you're going to have these induced dipole connections between matter, you have to kind of have a hand on polarizability. So polarizability increases with increased number of electrons. So remember we a little bit ago looked at H2O and H2S and H2SE and H2TE. So tellurium would have the most number of electrons. So that's not a good example because it would be partially, that's not a good example. Now let's look at Br2 and I2. Okay, so iodine has more electrons than bromine. So the I2 molecule would be more likely to be more polarizable. Yep. Let's see. The larger atoms, electrons are further from the nucleus and less attracted to the nucleus. Number of electrons increase with increased molar mass. And this kind of goes along with this. If I were to take this and to add more carbons on it, you've got more ability to polarize that molecule. All things being the same, larger structures are more easily polarized. Okay. Let's see, van der Waals forces. Make sure I get this right. Oh. So I don't use the term van der Waals forces much, so I'm pausing to make sure I get it right, what I'm saying on the slide here. Everything but ions. So that's the ordinary dipole-dipole, but no hydrogen bonding, dipole-induced dipole that needs a mixture, and induced dipole, which could be a mixture or a pure substance. Again, I don't use that term very much. Pause. So that's what our book uses it for, but sometimes van der Waals forces are a fourth synonym for induced dipole. Just like you need another word for,
Yeah.
right? Okay. Cool. So we talked about taking a molecule and looking at the polarity of the chemical bonds and then coming up with a net dipole moment. And so up here we have net dipole moments. Remember, if there is no net dipole moment, then it's nonpolar, right? So here, maybe not so surprising, is in a molecule of F2, notice the percent of intermolecular bonds keeping that together is dipole is 0. That makes sense, right? Yep. HF, 18%. It's a polar molecule. The other 3 are actually polar molecules. Notice then that the amount that kicks in with those, remember dispersion is the same thing as induced dipole. So induced dipole kicks in the larger the molecule is.
Okay.
So, yep. Because chlorine is the lightest, all by bromine followed by iodine. So even though HI is polar, and you definitely have this dipole going on, it's actually the induced dipole, or the dispersion forces that.
Okay.
So the last column gets back to kind of one of the things we talked about in Chem 1. What is the latent heat of vaporization? So how much energy do you need to jack in order to have 1 mole of this go from a liquid to a vapor? That's what that is. So here we have, when we're talking about how the heat of vaporization is an indication of the amount of intermolecular bonds. So is the boiling point temperature. Cool. So this actually is kind of an interesting little, let me go ahead and put all these up here. Along the x-axis down here, we have 7 substances. And for those 7 substances, what your author has done is have little bars to indicate what 4 forces are going on. So it's color-coded. So at the top, you can see the yellow and the light blue is the total forces. And yellow is induced dipole. So for argon, all you're going to have is induced dipole. Carbon monoxide, also induced dipole. I'm kind of surprised that's not carbon monoxide. Didn't say that was a polar molecule. This kind of surprises me.
Yeah.
As I'm looking at it this semester anyway. I think that's weird. HI, we said that the iodine's like pretty darn heavy, so again you have a lot of the induced dipole going on. But finally you see just a hint of the dipole. Well, no. Here finally we see at least a little bit of dipole, more dipole, okay. For these last 2, of course, we have hydrogen bonding going on. And so a lot of that dipole is about the hydrogen bonding. Okay.
have then more than one type of intermolecular
Yes.
bonding for one type?
Situation,
Okay.
one chunk of mass, one chunk of matter, yep, that's stuck together, yep, definitely. Yep, so, we're on to a sinus slide. So we'll take a quick look at these. I did find them in my archives. I love archives. I didn't look closely at them, so these will be due on Wednesday. Let's see what hints I had. For each of these, describe the importance of those induced-dipole for dispersion forces, the dipole, and the hydrogen bonding. So it's kind of like that last one that we looked at. I think you'll be fine with that. I said draw Lewis structure. I'm not sure you really have to.
Yeah.
I think you might just be able to, but you should, the second one, you need to understand whether it's a polar or a non-polar. Yep. Keep in mind, all substances have London forces. Like 4 different names for the same thing.
Yeah.
London is induced dipole. Yeah, dispersion, London. I probably use those 3 names the same, you know. And then this is the second one. And I went ahead and drew benzene for you. I don't know if I did any others. Maybe I did them all. So there's benzene. The next structure's, there's benzene. Says when another atom or group of atoms is substituted for one of the hydrogens, the boiling point changes. Okay, so there's benzene. There's your baseline. So now notice the next one, we're going to change a hydrogen out and put a chlorine instead. So in organic chemistry, they hate drawing those little, you know. So in order to kind of show the alternating single, double, basically you have a 6-sided or hexagon here, and you do a circle in there to kind of show the alternating. So these are the same. And then, and we'll talk more about this in this class, but we just assume that we understand there's a hydrogens reaching off, there's a carbon at each of those vertices, and there's a hydrogen reaching off of that. Okay, so with that in mind, then we could show the second one with, instead of a hydrogen, put a chlorine. In this one, put a bromine, and in this one, actually put a hydroxyl group. So the regular boiling point of benzene is 80 degrees, and then 132, 156, and 182. So kind of as they're arranged, increasing the temperature at which it boils. So my thing in red here is that with this increasing boiling point temperature, you must have something going on with the intermolecular bonding. So you're just supposed to say something as to why that happens. Cool.